I think some of you guys are a little bit confused for this as to where you should start. Okay, there's a couple of different ways that you can do this. I am a picture person, so I would rather do this using a picture. And for my picture, I know that I have two groups in here. I always draw my big box that represents the whole entire sample set. Within that, I have a group of folks that like dogs or have dogs. I have a group of folks that have cats. I do have some people that have both. And most of you, the biggest question that I'm getting is, how do I know what number goes here? Well, think about your definition of or. Probability of a cat or a dog. What is the formal definition, the general rule that should always work? It's the probability of the cat plus the probability of the dog minus the probability of a cat and a dog, the overlap. So putting the numbers in that I have 60% own a cat or a dog. I have 34% have a cat. I have 39% own a dog. And then I'm looking for cat and dog. That's because these two, the cat and the dog together, all of those boxes should add up to 9. That's 73. That's a quite bit over that 60. So how many people or what percent is in both groups? So I'm going to put 0.13 here. Because 34 plus 39 is 74 or 73. That is 13 over. No? Okay. Now, we've got some more information to fill out my Venn diagram. You don't need to show this all here. You can just work it out and set up a Venn diagram. But if I have 39% in my dog circle, I already have 0.13. What am I missing? 0.26. I'm supposed to have 34% in my cat circle. I already have 13. What am I missing? 0.21. Does that all add up to 60? Yeah. So that means, what am I missing? The outside. The 0.4. Or if you want to see two digits, 0.40. So if I have the Venn diagram set up, I can actually use that and just go ahead and answer each question. What is the probability a randomly selected U.S. household owns neither a cat nor a dog? 0.4. You can do this here. I just wanted to make sure I wasn't forgetting. What's the probability that we own both a cat and a dog? What is the probability? Now for this one, again, we're going to have to back to some of our formal definitions. It says, what is the probability a randomly selected U.S. household owns a cat if we have a dog? That's the probability of cat given dog. How do I work that out? Probability of cat and dog goes on top. Good, divided by the probability of dog. Because and for given, and goes on top, this goes on bottom. So what is the probability of cat and dog? 0.13. What is the probability of dog? No. 0.39. Everybody that is in the dog category. Or you could even pull it right out of here. It said 39% owns at least a dog. So that means when I divide that out, that's what I get. Okay? Now these probability rules, this is one of those units where the general rules themselves are super duper easy. If I give you a setup of a Venn diagram and ask you to answer these questions, you could probably do that without much problem. The issue with this class is being able to take those rules and apply them in various situations. how they interact with each other, how do they affect each other, what's going on. And that's what makes this class hard. Now, I know that we're coming up to the end of the marking period. It's actually Friday, right? You guys know that? Friday is the end of the marking period. I think it's an important thing to kind of make sure everybody understands that this class, you need to kind of think about when a lot of people are like, well, what can I do to get an A? I'm not happy with my B. What can I do? Well, what I've got in the back of the classroom is actually what the county puts out for what you should be able to do for each grade. And if you take a really close look at that, for an A, can somebody read me what it says for an A? On the far right? Okay. You need to ask yourself, are you in that category? If you're not in that category, you probably shouldn't have an A in the class. What does it say for B+? Okay. She's a very good reader. Thank you so much for that. But yeah, and then what is a B? That's a solid B. So you guys need to understand that it's not just about how do I get the grade that I want. You actually have to be able to kind of handle all of the different levels of thought with this. In this class, and I am not making it so that an A, I'm not teaching you things. Please understand, I'm not expecting you to know how to do things that I never taught you. I'm not expecting that. But what I am expecting for you to do is to be able to apply problems in various contexts. And I'm being 100% honest with you when I say the Khan Academy homework is not going to be enough for that. That will get you to the C level. The Khan Academy should get you to the C level where you understand the general rules and you can do them, maybe make a couple mistakes here or there, but you can get through it. If you want to get that A, you need to do additional practice problems, which are found in the book. Odds are in the back of the book. I've been posting additional practice problems, full solutions online. You need to be practicing. And statistics is not just about, it's like the flip book. Knowing everything that's written on the flip book should get you a C. That's just basic concepts. So that's the purpose of the flip book, is to get you to at least understand what you're supposed to know. Beyond that, start making the connections. Your quizzes, doing well on your quizzes, you should be able to get a B in the class, because literally I turn around from class. Most of your warm-ups, have you noticed, are pretty much your quizzes. That's a B. The A's come from the tests themselves, is being able to differentiate between which objectives that we have to do, how to apply things when it's all mixed up. And if you want to do that, when it comes time for studying for the test, that means go back and do practice problems. I love your book. Your book is so wonderfully set up. Literally, go to the review portion of that unit. Do it. Okay? Because I just know that right now, a big heavy focus is on grades. It should be on what you understand and what you can do. And then if your grade matches what we've got described up there, then that's great. If you think your grade does not match what's described up there, then we really need to talk. We need to figure out what's going on. Okay? B's are wonderful grades to have for this class. This is a challenging course with a lot of critical thinking, a lot of applications, a lot of when on earth do I use each of these different rules? Okay? That's why it's a weighted class. It counts as an A. Okay? All right. So, anybody have any questions or anything about that? Yes. I am going to do my hardest to do my darndest to get the quiz in on this quarter. Your quiz is scheduled for Thursday. Basically, all we're going to be doing on Thursday, I'm going to spend as much time as you guys want doing practice problems before the quiz. Okay? And then the quiz is the last thing I have scheduled for that day. No new material. Don't worry. It's just practice. That should be, as long as I have a majority of people showing up for school that day, please show up for school that day. it will be on the first quarter. Okay? It's just if I'm going to have to go back and do a ton of grade changes, I'm not going to put it on the first quarter. Grade changes would be people making up stuff. Okay? So that's what you have. What you have left grade-wise for this quarter is your Khan Academy assignment, which is due tomorrow night, and your quiz. Okay? All right. So let's keep going. We done. We did this. Today, we're going to go a little bit closer into some of the different things that we get to look at for probability rules, emphasis at look at. We're going to be talking mostly about how you can draw pictures to describe these things. Because probability is very, very complicated to sometimes understand what's leading to what. But if you can put it in a picture form, that's usually a good start. And just make sure everybody knows, if you're plugging in your phone, your calculators to be charged, just make sure it's plugged in the back. Okay? Otherwise, it's not going to charge. You should see a little light on the right-hand side. Okay, so we have done a couple of pictures in here. We talked about Venn diagrams. We've talked about probability tables. And those are awesome tools. They're just not always going to work. Before we do anything else, it's very important. I'm so happy on your guys' quiz. I don't think anybody in any of my classes wrote for the first question both independent and disjoint. That's a win, considering we've said that a bajillion times that you can never be both. The reason for that is what each of those words talk about. If something is talking about independent, the basic definition of that says that one event is not going to affect the outcome of another. They don't affect it. That doesn't mean they don't cause it. One of the biggest issues with the quiz was the first problem where it was asking independent, disjoint, or neither or both. If you think about it, your mode of transportation, your grade level does not determine your mode of transportation. Freshmen are not forced to ride the buses. Seniors are not forced to drive to school. But does your grade level affect how you get to school? Does it play a role in how you get to school? Yeah, because somewhere along the line, you get your driver's license. Or your friends get their driver's license. You get access to a car, have a car, your friends. Your transportation level changes, or mode changes based on your level of your grade. So when it was talking about junior and walking to school, was that the first question? Your probability changes as you move through the different levels. Your grade does not determine how you get to it, and that's, I think, where we've got a lot of people getting the hiccup. Your grade does not say you travel this way. But there is some linking that goes on between that. And really, the linkage is how old you are. As you go through your high school years, you start having different opportunities available to you. So those things do, in fact, change. Another example would be choosing to wear tennis shoes and completing your homework. I don't know anybody whose homework completion depends upon what their footwear is or is not at that moment. Although if I'm wearing like really uncomfortable shoes, I'm not going to do anything except take them off, then do stuff. Does that make sense? I mean, it's kind of like one of those things where it's like, well, duh. Of course, your shoes should not affect your homework completion. Your choice in pizza toppings should not affect whether or not you're on time to class. Duh. Type stuff. Okay? Whereas disjoint. Give me another word for disjoint. Mutually exclusive. Basically, both, that means that what's true. Both of those phrases mean what? Can't happen at the same time. So for disjoint, that's where they cannot happen at the same time. You cannot be in Algebra 1 and AP Statistics at the same time. Those are disjoint. And putting together what those definitions mean is what makes it so that you cannot be independent and disjoint at the same time. Because the idea of independence is talking about the probability of B given A occurred. And if I'm doing that formula, probability of B given A occurred, what goes on top? B given A. B and A. But disjoint says there is no and. You're not in both groups at the same time. So that's why those guys cannot happen at the same time. They can, however, be no to each of them, neither disjoint nor independent. That does happen. Okay? All right. So take a look at this table. If I were to look at this table, what would you consider to be disjoint? Being a Democrat and a Republican? Or independent? Because I'm not going to fall into multiple of those categories at time. I mean, yes, you can have viewpoints that stretch over the top, but if you're going to be voting, when you vote, that's what they look at. They mark you as a Democratic voter, a Republican voter, or an independent voter based on your big ticket people. And you are literally, once you become a voter, on a list somewhere defined by that. What else is disjoint? Gender. Because you, according to this table, are not going to be male and female at the same time. Okay? Now the question is party affiliation independent from gender? What do you think you might want to do with this table if I want to answer that question? If I had asked you to draw a graph of this, a bar chart or a segmented bar chart, what would you do first? Find your conditional distributions, which rely on the totals. Got to find your mark. Means add them up. And then the definition of independence. Can somebody give me our classroom definition of independence? Mathematically, probability speaking. What's within 2%? We had a formula. We had an equal sign involved. There you go. Probability of A given B is equal to the probability of A. So when we're talking about independence, we're dealing with this one main idea. Probability of a second event occurring given the first has to be just the probability of the second event, whatever letters you chose to put there. I'm writing it this way because a lot of people get confused sometimes when I have A's and B's. I want to make sure that you understand that it's what's in this first spot. That's what's crucial. These two have to match. So I could talk about the probability that you're a Democrat given we're males. So 32 over the total for 32 and compare it to just the probability of Democrat. Or I could compare it to the probability of Democrat given female. I can compare it as long as that first piece matches in both of them. Okay? So what do you think this is going to be? Not independent? Independent? He was going like this. I'm not trying to... What does this mean? Okay, why don't you actually try plugging numbers into your calculator? What? This is a good example of tying back to the difference between knowing the general rules and being able to actually do a problem with them. There's all sorts of different ways that you can answer this question. They'd all give you the same answer. Or they should. Yes or no? Not independent, right? Not equal here means not independent. Please, please, please don't ever use the word dependent, prove, cause. Don't use those words in this class. Everything in here is a spectrum. All we're going to say is that something is not independent. Something, I either have evidence to support a claim or I don't have evidence. Okay? Those definite terms are dangerous. So for this guy here, there's a lot of different ways that you could have worked it. I would have worked this problem saying, for example, here, why don't you give me which one of your probabilities? So you did 32 divided by 94, so I'm assuming that you did male Democrat. So you did probability of Democrat given male, and what did you compare that to? Just given female, okay? That's fine. Those two first letters match. You could have compared any of those to the general probability of Democrat. Any of those match. And if you have anything that shows up as not equal, if we have this is not equal, let me tell you, this is not going to be equal either. Neither is this. Okay? It's not going to be one of those things, well, it worked here. When I did it, it worked, but when this person did it, it didn't work. It always is going to come up with the same idea. So the probability of Democrat given male, that's the 32 over the, 94? Versus the probability of Democrat given female is 41 over 92. So those guys are not within 2% of each other. And you would just simply say, so you did, 32 over, what was the total for males? And you did 41 over 92? That's it. You would say, not independent, and that is your work for it. That's the work that I would require you to be shown here. Whatever you chose, they're independent. If they're equal, they're not independent. Okay? Yes. Yes, the 2% is like, we're not going to get it exactly because our populations aren't going to be the exact same size. So we say, when I say equal, I mean within 2%. Okay? And that's simply because for mathematical reasons. And all you need to do is you need to find one instance where they are not equal, not within 2%, in order to say not independent. You have to check all of them to say that they are independent, which is a big pain in the tuchus. So what I usually do is I look to where I think the biggest discrepancy is going to be. Grab the most obvious one and go with that. Okay. So slightly different one. Here we're talking about blood pressure and cholesterol levels. I don't know why that's a hard word for me to say. I was having a really hard time with that during first period today. Which characteristics are disjoint? High blood pressure and okay blood pressure. What else is disjoint? High cholesterol and okay cholesterol. You're not going to be, I don't think, I mean, I'm not a doctor or anything, I don't think you can have high cholesterol on one half of your body and okay cholesterol on the other half. I don't think it works that way. Could be wrong. All right, so those are my disjoint things. What we have here that's different with this table versus the previous one, the previous table had counts. This works exactly the same way. It's just talking about percentages, your probability out of the whole group. Because if I were to add all of those four numbers up, what should I get? 1. So dealing with what I told you I expect to see for your work for this one, go ahead and try that. You are not just going to say, oh, well, 11.11 is not 0.16, so no. You're not going to say 0.11 is not 0.21, so no. It's never that easy. What might you want to do first for this? One more time. Totals. Just to make your life easier. What do you think, yes or no? Ooh, that's an easy one. Nobody's going to guess. They're not independent. You're like, oh, thank God. Oh. I don't need your numbers. I just want to know, what did you compare? High blood pressure. If you did 11 over 32 and 16 over 68, that translates into saying, I compared what is the probability of high blood pressure given high cholesterol, and compared it to the probability of high blood pressure given okay cholesterol. I'm wanting you to use those words because I want you to see that first piece, the probability that I'm focusing on, the high blood pressure, is the same for both of them. It's the conditions that change. Okay? You guys all look like you're so dead right now. Hello? Yes, ma'am. Okay. Take 0.11 divided by 0.32. No, literally. And 0.16 divided by 0.68. Are those the same? No. And really what you can do here, there's a lot of different combinations that you can do. You can do any combination that boxes it out. What I mean by that is you see how 11, 0.32, 0.16, 0.68 make a nice patterned box? I am not going to do 0.11 over 0.27 and 0.16 over 0.27. That does not make a nice box. A nice four-corner box. I can do 0.52 over 0.68 and 0.73 over 1. That makes a box. I could even do 0.52 over 0.73 and 0.68 over 1. That makes a box. You can use any four numbers that make a box. Okay, as long as you're just following the same pattern. So there's all sorts of different ways that you can do this. I would have said no because, and again, you want to be able to write your symbols. So you would have done probability HB given HC, probability HB given OKC. Okay? So you need to be able to write that out to be able to communicate what it is that you are doing. Remember, this class isn't just about getting the probabilities right. It's about being able to communicate what process you took. All right. So these are in your notes again. I want you all to work through problem number 2. Basically, I'm going to show you the minimum work that I would expect to see for this. Because remember, it's not just about your answers, but it's about being able to communicate where your answer came from. So this is what I did. For A through E, That is the work you have to show. If you do not show those fractions, you will not get full credit. I do want to take a moment to say, though, if I'm giving you things in decimal form, like I'm giving you a probability or I'm giving you a percent, you don't need to translate those into fractions. But these start off as fractions to get the percents. And then if you look at F, you don't need to have picked the exact same comparison that I picked. I said I'm going to compare the total probability that they had breakfast. So that's 191 over 331. Comparing that to the probability that they ate breakfast, given that they're female, so that was 125 over 199. I used this, 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 and this for my box. You have to write this because this is your formal definition for independence. You've got to tell me what those things represent. And you should notice that when you do that, whatever this first letter is, that should match for both of them. Pretty much any combination works as long as that first letter matches. Remember, when you're talking about given, the given should be your denominator. Oh, just because the example that they chose, the way that they chose to do it, was they compared. And you could have done that. I could have compared this to the probability of having breakfast given you're a male. I could have done that, and that would have been 66 over breakfast 191. Which would have been, did I have that up here? I didn't. So I'd have to calculate that, and I would see that that's still not going to be equal. Okay. Yeah, sorry, I was trying to figure out which direction. Thank you, I appreciate that. Because we have to follow the same pattern. So that's what I would have had to use. So you could have used those four. Okay. Any other questions? All right. These are your table problems. We've seen some Venn diagram problems. What's coming up next is a tree diagram. Now, this is also the next problem in your notes. Okay, so just go ahead and read it, whether you want to read it from the board or in your notes. I don't care. If y'all have ever traveled with planes, you know this is a huge issue. You and your bags do not move at the same rate. You can book it, they can't. Yeah, the tree diagram. What was the concept? Problem is I've done these problems so many times, it's hard for me to kind of say exactly when what was done. So it wouldn't have been pre-calc. It wouldn't have been last year is what I'm saying, so you're not getting it confused with that. Neither can I. We're going to talk about it here. It's okay. It actually might have been a problem very similar to this. And that's the idea. Oh! It was on the review for the last one. The chapter 13 review where we had yes, you're not going crazy. I don't know exactly. Yeah. I have no idea what you're talking about. Okay, let's just go through this. A tree diagram is a really, really, really beneficial way to display your information when you know for a fact that your probability changes based on what's occurring. The thing that you need to do for a tree diagram, and tree diagrams can be vertical, they can be horizontal, they can go bottom up, top down, I don't care. It's whatever fits the space and helps you think through. When I'm doing this problem is talking about computer chips from different companies and whether they're defective or not. What is going to happen first? The company that makes them or whether they're defective? The company that makes them. So what I mean by that is I am going to start my tree diagram with the three choices of company A, company B, or company C. That's really going to irritate me. That's not lined up nicely. I like graph paper for a reason. Now, by the way, when we do Venn diagrams, you have to make sure that you're coming back to this. Oh, I know what you're talking about. You're talking about the design of studies. No? Okay. Okay. The thing that you need to understand is when these lines come from a common point, they should add up to 1. So what is the probability that we came from company A? 0.1. What is the probability we came from company B? Elise, for now, just focus on this one. I know you're just distracted. And for part C, from company C? 0.7. Do you notice that all of these come from the same point? So those should all add up to 1. Now, we've decided whether or not which company it came from. And then within each company, they're either going to be defective or not. And I don't care what notation you use. I don't care if you use D complement, defective, D, okay. I don't care. Whichever one you want to do. From company A, and notice I now have new spots here for each of this. From company A, what is the probability that a chip is defective? 0.04, which means coming from the same point, they should add up to 1. What is not defective? Okay. For company B, what is the probability of defective? 0.02, which means my probability for not defective. For company C, probability of defective. Good, 0.005, which means the probability of not defective. So when they share a common point, they add up to 1. But all of these share this point out here. And I can do that if I work my probabilities. How do I find the probability that it came from company A and it was defective? Multiply. So what do you get? What's 1 times 4? How many decimals do you have? 1, 2, 3. What is 0.1 times 0.96? 0.096. Sometimes it's a lot easier to just think. No, it's not. So calculate all those probabilities. Do our numbers match? What you got, what I got? And since this is the bottom of all of these leaves, they all stem from here, what should all of these add up to? 1. And look, 0.004 plus 0.96, 0.1. 0.004 plus 0.196, 0.2. 0.0035 plus 0.6965, 0.7. This times this equals this. Okay? Now the question this problem said, is it said a worker at a manufacturing firm discovers that a randomly selected computer chip is defective. So I know it's defective. What's the probability it came from company B? So if I were to write this in probability notation, how would I do that? Probability that it came from B, given that it's defective. What I'm focusing on, the main question, is the probability the chip came from company B. That's what I'm looking for. But I have this slight condition that it was defective first. So to calculate this, what am I going to do? Probability of B and D divided by the probability of defective. So B and D, that means company B and defective was what? 0.04. 0.004, sorry, one more zero. Probability of defective, that means all of my defectives. That one, this one, and that one. What is the probability of overall defectiveness? Starts with a point. 0.115. Good. And when you divide that out, that is the probability that it came from factory B or company B, given that we already knew it was defective. The tree diagram makes this calculation so much easier. Otherwise, I would have to do probability of coming from company A and defective, plus probability of company B and defective, plus probability of company C and defective. And that's just a lot of writing. And so I'll show you what that writing looks like. So we have our Venn diagram. If you had done it without a Venn diagram, you would have had to be able to calculate all of these guys separately. I definitely think the Venn diagram makes it easier. But even look at what they did. They write a lot more than I did. They wrote defective, okay, defective, okay, defective, okay. They actually showed the multiplication. I don't care about that. What I want to see, I'm going to assume if you work down this line that you are multiplying, but I need to see which proportions or what percents you have in each of those places. Okay? All right. So why don't you guys try this one from scratch? Again, this should be in your notes. Welcome to work together. I'd actually suggest you compare Venn diagram. Whatever your picture was, this isn't a Venn diagram problem, before you try to answer them. So do you guys think you guys got those two? So let's take a look at my answer. This is what I got. Take a look at those problems. For A, there was actually no work you needed to do because they physically told you that your probability changed depending upon whether you made the flight was on time or not. So I don't need to calculate anything about being independent. They told me it changed. You use this method when you know they are not independent. You use a Venn diagram if you're talking about events that are all occurring at the same time, whether they're mutually exclusive or not. You can use a probability table for that as well. The probability table kind of merges the two. Disjoint events, independence. And I do not expect to see this. Okay, I would expect for work to see that. I just wanted you to know where those numbers came from. questions there? How are we doing with this? It's like, well, it's easy when we're doing it together. It's when I have to do this on my own or in quizzes and tests that it gets hard. Okay. And just to kind of give you an idea of the textbook likes to make things a little bit way too spelled out, literally. Luggage makes connection. Luggage doesn't make connection. Yeah, I don't know. No. We don't have time for that. Ain't nobody got time for that. And I don't care if you summarize this with T complement. I don't care if you say on time, not on time. Luggage makes it, luggage doesn't make it. I just like the C because it means not. Phone away. And they get very, very wordy with their explanations. Okay. No matter what, probability, we've already talked a little bit about this during Flex yesterday. When we have the card problems, that stuff, I need you to understand that when it says you are dealt a hand, anytime we're talking about a hand of cards, is that with or without replacement? That's without, because in order to have a hand of cards, I have to give you a card in your hand and then give you another card while that first one is still in your hand. That's why they call it a hand of cards, because you're holding multiple all at once in your hand. Yes. So when we talk about dealing a deck of cards, a hand of cards, that always is going to mean without replacement. But you need to be careful with this, because everything changes. Literally, everything changes. No matter what I'm talking about. This says the first heart you get is the third card that's dealt. So I'm looking for the probability. What happens on the first one? Not a heart. What happens on the second one? Not a heart. What happens on the third one? Heart. So what is the probability? How many cards are there in a deck? 52. And of those 52 cards, how many of them are hearts? 13. So that means how many of them are not hearts? 39, yeah. So that's the probability that the first one is not a heart. Now, one card is out. How many cards are left in the deck? 51. How many of those cards in the deck are now not hearts? 38. Now, how many cards are left? 50. How many of those cards are hearts? This is the work you need to show. And technically, this is not the correct way to write it, because this would be with replacement. What we're talking about, what's the probability of getting a heart given... Actually, no. It's that was correct. That was correct. It's just it's conditional, so it makes it a little bit weirder to write. So, no, that's right. That's fine. It's the right way. Yeah, because if I write probability of heart given not heart and not heart, then that would have just been this. So yeah, that's fine. What do you get? Out to 4 decimals, please. 0.1453. The work I expect to see is this. That right there. Okay, so the probability that the cards are all red, that means I've got a red heart, a red card, another red card. How many cards do I have? In each one of these guys, we're starting over again. So how many cards are there in a deck? How many of those cards are red? Okay. Now, the next one. How many cards are left in the deck? Considering I already got a red one here, what's the probability for the next one? 25. Now, how many cards are left in the deck? 50. How many of the ones left in the deck are red still? 24. These are each conditional probabilities. Probability of the first card is red. Probability of the second card is red, given the first one was red. Probability of the third card is red, given the first two were red. And then give me that to 4 decimals. Yes, it is. Sorry, I was looking at the wrong question. She's like, no, I felt good about that one. I want you guys to try C, and because I'm evil, D. D has at least 1. No! The same way. What did we do at least 1 before? We said 1 minus the opposite. 1 minus no aces. So that's just you're saying no ace, no ace, no ace. Now she's just saying math terms. The denominator, the numerator. You're overthinking it. No, you cannot take a test together. All right, let's take a look at your answers. So the probability you get no spades means not a spade, not a spade, not a spade. So I actually got 0.4135 is what I have. And then just in words, probability that you have at least 1 ace. How would you calculate that? 1 minus the probability, which is no aces. Okay? So no aces means the first card's not an ace, the second card's not an ace, the third card is not an ace. So I worked it out the exact same way. My work looks the same. Got 0.2174 collectively. Because we're talking about not an ace. There are 4 aces, so that means there are 48 that are not aces. Okay? How are we doing with this? Sola's doing great. Good job, Sola. All right, so what we're going to do now is I want you guys to do practice problems that are in your notes, problems 6 through 8. 6 through 8, please. You guys have a quiz next class. You have your Khan Academy assignment due tomorrow night. And again, we will just finish these up next class.